All right, good morning, everyone. As our situation keeps evolving, I'm continuing to adjust and try to make things work for you. I've received some feedback, so you'll see in the post some time changes on when things are due. But in general, I didn't receive any major questions yesterday to alter things. If you do have requests or things you want to change, please do let me know. Email me or text me or call me, and I'm happy to adjust and figure out what works best for you. But please do let me know what you think you're needing. For today, we're going to continue with Unit 10, talking about infinite series. We're going to be looking at the nth term test for divergence and the integral test for convergence. If you recall back in 10.1, we learned sort of the first theorem of a set of theorems I said we were going to learn this unit. And it said this: if you have some sum of a sub n, where a sub n is the term at the nth term, and it converges, then the limit as n approaches infinity of the term, so the limit of the term formula as n approaches infinity will be 0. But I said be careful, because the converse is not true. If you find that the limit of the term, nth term, is 0, that doesn't necessarily mean the series converges, because the limit of the nth term could be 0. But there are ways, as we'll see, that the series still won't converge. However, this theorem does lead us to an important conclusion, and the first in a group of useful tests that we'll use to determine whether or not a series converges or not. All right, here it is. We saw it on Friday. It says that the limit as n approaches infinity of the term, so the nth term as n approaches infinity, if it doesn't equal 0, so if it's 1, -2, half, pi, does not exist. So if it's not 0, then that does mean that the sum will diverge. We call this the nth term test for divergence, okay? So this tests whether or not a series diverges. The nth term test for divergence is also called the divergence test, or the term test. I'm doing air quotes over there, I guess you can't see. Term test. It is quite simple, frankly, to use. If you have a series that you're looking at, and you can determine that the limit of the term a sub n as n goes to infinity is anything other than 0, okay, the limit is anything other than 0, the series diverges. However, if the limit is 0, what does that tell us? All that means is we can't be conclusive about convergence and need to choose another test. We'll learn them. We're learning one today, the integral test. But if you do get 0, basically it says, okay, great, can't tell it's divergent, move on to a different test. But this is kind of a first sort of stop in the process of determining convergence for a series. All right, let's practice with this. All right, here we go. Determine if the following series is divergent, or state why we cannot be conclusive about convergence. All right, so I'm looking over here. Looks like I've got to maybe help us if we zoom in a little bit. I'm looking at a series over here. Great. This represents my a sub n term. So a sub n is 3n squared plus 2n over sine of n plus 2. I want to take the limit of that. So I want to take the limit as n approaches infinity of 3n squared plus 2n over sine of n plus 2. All right. So what do we know? As n goes to infinity, up here in the numerator, if we're trying to figure out our n behavior model as we find limits, that's often one of our things that we do. The n behavior model up here will be controlled by 3n squared. So we want to take the limit as n approaches infinity of 3n squared over, because 3n squared is going to grow much faster than 2n. Down here it gets a little funky. Sine of n plus 2. Well, as n changes, sine is just going to go between -1 and 1 plus 2. So really, this denominator ranges between 1 and 3, right? But it's finite. Essentially 2 controls it because 2 stays bigger. We can use that as our n behavior model. As n goes to infinity, what do we get? Well, this numerator goes off to infinity. So it approaches infinity. What does that mean if this limit approaches infinity? Well, the limit of a sub n, our nth term, as n goes to infinity was infinity. That's not 0. So this means the series diverges by the nth term test for divergence. Whenever I do these videos, I feel really lousy about my handwriting. Wish I'd paid more close attention growing up to that. Well, there it is. Series diverges by the nth term test for divergence. Let's check the other one. This looks a little interesting. We have we're coming across factorials for the first time in this unit. Just as a reminder, if we're looking at like a factorial, what does that equal? That equals a times a minus 1 times a minus 2 all the way down until we multiply it by 1. Okay? I guess we say multiply by 0. Factorial, 0 factorial, not 0. 0 factorial, which 0 factorial is 1. We can talk about that later. Alright, so let's take a look. So we need to find the limit as n approaches infinity of 2 times n plus 1 factorial over 6 n factorial. Interesting. Okay. Now we simplify this. This is the limit as n approaches infinity of 2 times, okay, n plus 1 factorial is really n plus 1 times n factorial, right? Because then n factorial will keep multiplying itself down. N plus 1 factorial is n plus 1 times n minus 1 times n minus 2 times n minus 3. 6 times n factorial, well, that's just 6 times n factorial, and I'll see that this multiplication thing that this represents, n times n minus 1 times n minus 2, will cancel out with n factorial down here. We'll divide away and leave us with the limit as n approaches infinity. Ooh, voice crack. Limit as n approaches infinity of 2 n plus 1 quantity. And as n approaches infinity, this will approach infinity. So that means our series diverges by the nth term test for divergence. All right. So there are 2 examples for us to see that use the nth term test for divergence. All right. Some key takeaways here that I want us to take from this. 1, the nth term test for divergence tests for that. It tests for divergence, not convergence. We actually cannot tell convergence from this test. That's it, just divergence. If the limit of the nth term as n goes to infinity is 0, it does not imply convergence. We need another test to test convergence. All that means is we choose another test. Think about this one as your first line of defense in determining whether or not series or things converge. You try it. If it fails divergence, then great. If it gives you 0, you got to say, okay, we're inconclusive. We got to try something else because the limit of the nth term as n approaches infinity was 0. All right, here's what I'd like you to do. I want you to take a look at the set of practice problems that are at the top of the next page. I want you to take about 5 minutes or so, pause the video now, do the problems, and come back and check, please. All right, let's rock and roll. I'm going to zoom out just a tiny bit to be able to see stuff. Always adjusting and trying to figure out the best way to do this. Maybe that's a little better. Okay. Remember, essentially what we need to do is find the limit of the nth term rule that we see here. All right. Our nth term rule here. We can see we need the limit then as n approaches infinity of 1 plus 3n squared plus n cubed over 4n cubed minus 5n plus 2. All right, let's figure out our n behavior model. That's supposed to be an arrow. Let's figure out our n behavior model then as n approaches infinity. What's going to win up top? These are basic polynomial kinds of things. So 3n squared, nope, that's smaller than n cubed. So n cubed wins up top as it grows. In my denominator, 4n cubed wins down there. So 4n cubed down there. So this is going to simplify to 1/4. So my series diverges by the nth term test for divergence. I know that's a lot to say, but I want you to keep saying it. In fact, if you're feeling really excited, please just say it to yourself at home until you get comfortable with it, because we'll be seeing it a lot. All right. So let's move on to our next one. All right. So our next one says our series from 1 to infinity is 1 over n squared. We'll actually spend some time with this one in a little bit, in a deeper kind of way. Let's take a look. So I come in here, I say, all right, I need the limit of the nth term, so the limit as n approaches infinity of 1 over n squared. That was actually relatively short. As n grows, 1 over n squared grows. So this has a limit of 0. What does that mean? We cannot conclude divergence or convergence because it's not spelled with a Y, because the limit as n approaches infinity of a sub n equals 0. There we go. All right. Moving on over. Let's take a look. Okay. But we got more factorials in this one. Let's see, we have the limit then as n approaches infinity of n factorial over 2n factorial plus 1, right? All right. Kind of interesting here. If we think about and compare the sizes here, we have n factorial, so that's going to be n times n minus 1 times n minus 2, and so on, all the way down to 1. And 2 times that value, so these values are really the same as they grow, plus 1. Well, if n is growing to infinity, this plus 1 doesn't really matter, right? So the thing that controls us here in terms of our n behavior then, our n behavior model will be as n approaches infinity, n factorial over 2n factorial, which gives us a limit of half. So our series diverges by the, say it with me, nth term test for divergence. Hope you said it at home. All right. We can letter these. So this was A. This was B, here was C. I want to put D down here. D gives us this quantity up here, or this here as our A sub n. So I really want the limit as n approaches infinity of n plus 2 factorial over 2n factorial, right? All right, when I rewrite those factorials, as I did in my example, I'll have, this is really n plus 2. We want to try to get an n factorial to appear here so we can cancel some stuff out, and we can. N plus 1, n factorial, right, because n plus 2 factorial is really n plus 2 times n plus 1 times n minus 1, and so on, all the way down, over 10 n factorial. We'll divide those away, and we'll get the limit as n approaches infinity of n plus 2 over times n plus 1, over 10. And as n goes off to infinity, the numerator is going to win, so this approaches infinity. And we can say then that our series diverges by the nth term. Can y'all see that? Yep. Test for divergence. There we go. All right. So there's the nth term test for divergence. Really quick and sharp for figuring out whether or not series diverge, right? Okay. Let's take a look at our next test. Now I'm not going to post a proof of this in this video. Sorry. But if you go to my website, I will post a video and a link that does prove why this test works. It is actually a fairly intuitive one to prove, especially when you have some visual aids. But here's what it says. Let's say we have some sequence of terms, and they're positive terms. Right? Suppose then that the sequence, the a sub n term in that sequence, is equal to some function at that n value also. So basically this sequence and this function's values line up, where f is continuous, positive, decreasing function for all x is greater than or equal to n, where n is some positive integer. All right, break that down for a second. You'll see more of this in the proof. Essentially what we're saying is, let's imagine some situation where we have a function where x is some positive integer value, and you have a function that is positive, continuous, and decreasing for x is greater than or equal to that n value. So something like this might work, okay? So we gotta imagine functions that have that kind of behavior, that continuous, positive, and decreasing when x is greater than or equal to some value of n, okay? If you have all that, then the series from n big N to infinity of a sub n, little n, so starting at that n value, the series and the integral from that big N value to infinity, and the integral either both converge or both diverge. All right? So if you have a continuous positive decreasing function that is essentially the same as the series, then the series and the integral converge or diverge. They will do the same thing. This is called the integral test for convergence. Basically, it says, hey, if I know that my series is essentially a continuous positive decreasing function and I take its integral, it will tell me whether or not that series converges or diverges. All right? I want to start with two of the most demonstrative applications of this test. Oh, I think I missed an S there. No, it's fine. Determine whether each series below converges or diverges using the integral test. Okay, so I'm going to find the series, whether or not this series, from 1 to infinity of 1 over n, converges or diverges. Now my nth term test, as n approaches infinity, would tell me 0. Inconclusive, right? So I have to use a different test. I'm going to use the integral test. 1 over n, as n increases, is continuous, positive, and decreasing. So I can use my integral test. All right, what does the integral test say? It says I can turn this thing into the integral from 1 to infinity of 1 over, I'm going to call it 1 over x to make us recognize the difference here, dx. All right, essentially you go, Markwalter, this is an improper integral. And you're right, it is an improper integral, so we'll use all of our improper integral rules. I'll define a limit, I'll call it as c approaches infinity of 1 to c of 1 over x dx. All right. I take my antiderivative, but I keep my limit. So my limit as c approaches infinity, the antiderivative of 1 over x is the natural log of the absolute value of, well, of x evaluated from 1 to c. So after I've done my antiderivative, I can plug in my value. So the limit as c approaches infinity of the natural log of absolute value of c, which is going to be positive. So if you want to drop your absolute values, you can, minus the limit of the absolute value of 1. But there's no c there, so that'll be EC. Let's see. The limit as c approaches infinity. The limit as c approaches infinity of natural log of c. As c approaches infinity, natural log will grow. So essentially this goes off to infinity. The natural log of 1 is 0. So what can we conclude? The limit here does not exist. So back in our earlier units, we would say that this integral diverges, okay? If this integral diverges, we can say the series n equals 1 to infinity of 1 over n diverges by the integral test. All right. Let's try the next one. So this one would have gotten a 0 for our nth term test, but based off of our integral, we found out this series diverges. Let's do this one. 1 over n squared. Okay, 1 over n squared, as n approaches infinity, it is decreasing because the denominator will grow. It is going to be positive. It's going to be continuous if n is above 1. So we are okay to use our integral test. The integral from 1 to infinity of 1 over n squared. I always want to use, well, you can use n if you want to. We just have to say dn. But I'm going to use dx's just to make it a little easier for us to follow. Okay? There we go. So this is going to be then, all right, I need to rewrite this as a limit. The limit as c approaches infinity of the integral from 1 to c of 1 over x squared dx. All right, I want to rewrite this. This is not a natural log antiderivative. I see a power down there, so it's going to be a power thing. So this is the limit as c approaches infinity. The limit as c approaches infinity of the integral from 1 to c of x to negative 2 dx. All right, this is going to be the limit as c approaches infinity of, I need to take the antiderivative of x to negative 2, so it'll give me x to the negative 1, and I'll divide by the new exponent, give me negative. All right, it'll give me that, evaluated at 1 and c. So this will give me the limit as c approaches infinity of, all right, when I plug in c to the negative 1, so that's going to be negative 1 over c. When I substitute in c in there, that'd be minus negative 1 over 1. All right, we have to evaluate that. Let's see. The limit as c approaches infinity of 1 over c, negative 1 over c, that's going to go to 0, right? Because the denominator is going to grow. Then I'm going to have 0 essentially plus 1. So my limit here goes to 1. Oh, cool. There's a number. So this integral, as we learned in our previous units, converges. So I can say that the sum then from n equals 1 to infinity of 1 over n squared converges by the integral test. All right. Cool. As a special note, we'll get to these a little more later. The series in A, 1 over n, is what we call the harmonic series. It's an incredibly useful series. It comes up a lot because essentially we are dividing by the next term, 1 divided by the next term every time, and so we have some special things to talk about with that one later. But both of these series are what we call P series. P series essentially have the form, as we'll talk about, n equals 1 to infinity of 1 over n to some power. Don't really need to know that for today, but we'll need it later, so might as well just go ahead and call it what it is. All right, P is some positive real number there. I guess technically it could be negative. It could be real number anywhere. All right. Wait, I lied. Can't be negative. Positive real number. Okay. Thanks for holding in there. We're doing pretty well. Let's take a look at 2 more examples, because basically we need to remember that all of our integral rules that we learned, can still apply even when dealing with these improper integrals, okay? So let's take a look. Determine whether each series below converges or diverges using the integral test for divergence. All right. 1 over n times the square root of n. As n grows, that will stay positive, and it'll decrease, and it'll be continuous if n is greater than 1. So I'm going to use my integral test. All right. What does my integral test say? It says I need the integral from 1, that's my place, to infinity of the function I have there, 1 over n square root of n. I did it again. Wow. X square root of x. Again, there's nothing wrong with saying n. I only use x is just because we're working with integrals, and I'll make it more clear that I'm doing something like different over here. Alright, dx. So I'm going to rewrite this as a limit. C approaches infinity of 1 to c. Now I got to think about this inside here. This is 1 over x square root of x. So it's really 1 over x times x to the half power dx. I recognize that these have the same base. I can write them as powers because if I can, I want to try to combine these two x things together so I don't have to use any more complicated kinds of antiderivative stuff. Alright, so this is going to be the limit as c approaches infinity, and we're from 1 to c, of 1 over x times x to the half. Same base, add the power, so this will give me x to the 3 halves dx. That'll give me the limit as c approaches infinity from integral from 1 to c of x to the negative 3 halves dx. Alright, what does that give us? I'll come back over here. I will do my antiderivative. I add 1 to the exponent, that'll give me x to the negative half power. X to the negative half power, right? But then I need to divide by the new exponent. My new exponent is negative half, so dividing by negative half is going to be the same thing as multiplying by negative 2, right? Okay, so I'm going to multiply by negative 2. Remember, you can always check these kinds of things by taking the derivative, get back there. I've done my antiderivative. I need to keep my limit, so I should have given myself a little more space. I'm going to rewrite this as the limit as c approaches infinity. That's going to be equal sign there. C approaches infinity of negative 2x to the negative half, evaluated from 1 to c. So this is going to be the limit as c approaches infinity of negative 2c to the negative half minus negative 2 times 1 to the negative half. Cleaning up some of this stuff, I get the limit as c approaches infinity of negative 2c to negative half. That's going to be negative 2 over the square root of c plus 2, right? Alright, as c approaches infinity, this first term will go to 0, leaving with 2, so I get 2. What does this mean? My integral converges. So the series from n equals 1 to infinity of n square root of n converges by the integral test. One more example, y'all. Doing great. Here we go. All right. This one's a little strange here. The series is 1 to infinity of e to the 1 over n squared. 1 over n squared is the power over n cubed. Now as n increases, yes, it'll stay positive. Yes, it'll be continuous if n is 1 or bigger. E to the thing will decrease to 1 because the power will go to 0, so it'll decrease to 1, and the numerator will go to 1, but the denominator will keep decreasing. So yes, this function does keep on the denominator keeps increasing to infinity, while the numerator goes to 1 as n goes to infinity. So what happens? We can use the integral test here because the numerator will go to 1 as n grows. The denominator will keep growing, so it does go to 0. It does decrease. So I can use my integral test, but my integral is going to look a little different this time because I'm going to have 1 over n squared in the power there of e over n cubed. I got to go, well, okay, well, how do I take care of this? First, let me rewrite it with my limits. And I can say, okay, what kind of integral antiderivative rules can I use here? Well, it's a little strange to tell here. It looks a little hard. What kinds of things do I have? I have integration by parts. Maybe it doesn't look super useful here. Doesn't look like I can use partial fractions. But u substitution is often good for these kind of funky looking ones where we have something inside of something else, and I see that here. So let me do u substitution. Let me say that u is going to be 1 over n squared, which I know is n to the negative 2. Let me take the derivative. I called it n again, didn't I? Wow. Well, for now, we'll leave it as n. I'm going to call this dn then dn. Not great notation. Should have changed them, but we'll leave it for now. Okay. So du dn is equal to the derivative of n squared is negative 2 n to the negative 3, right? Which is negative 2 over n cubed. Alright, when I do some rearranging here, remember I want to solve for dn. So if I solve for dn, I know basically now that du dn is negative 2 over n cubed. If I multiply dn over here, multiply these things to the other side by using the reciprocal, I would have n cubed negative n cubed over 2 du equals dn when I rearrange that. I also know for u substitution I need to change my endpoints, right? By using my u formula here. So my endpoint when n was 1, my u equivalent is going to be 1 to the negative 2. Oh, it's actually also going to be 1. Alright. My upper endpoint was c. So when n was c, when I plug n is c in here, c to the negative 2, that'll give me that u is equal to c to the negative 2 power, which is 1 over c squared. Okay, so now I know all my substitution stuff. So I want to come back to my integral, and I'm going to say that this is the limit as c approaches infinity of my new endpoints. My lower endpoint, which was 1, when I plugged n equals 1 in here, 1 to negative 2 became 1. That's there. My other endpoint became 1 over c squared. Alright, we'll take care of that later. Don't worry about it now. I now know that u is 1 over n, so this will give me e to the u over n cubed, where dn is negative negative n cubed over 2 du. Simplifying this up, I would lose my n cubes and I get negative half left. So I get the limit as c approaches infinity of the integral from 1 to 1 over c squared of negative half e to the u. Because those will cancel out, we'll get negative half. The e to the u still stays there, du. Alright. So what's my antiderivative of negative half e to the u? Well, it stays the same. So this will be the limit as c approaches infinity of negative half e to the u. That's the antiderivative of negative half e to the u. Evaluated from 1 to 1 over c squared. Alright, well, as c approaches infinity, 1 over c squared, that approaches 0. So really I'm going to be substituting in 0 there. So I would end up with negative half e to the 0, because the c approaches infinity, 1 over c squared approaches 0, and I plug that in first, minus negative half e to the 1. A little line there. So that's my my limit. I could clean this up, so this would be negative half e to 0. So it's negative half plus half. So I'll bring that up here. This is really, if we simplify, negative half plus half e as my actual limit. What does this mean? Well, I did not give myself great space here. Sorry, y'all. What does this mean? So, if I sort of box out here, all that stuff over here is actually my integral work. over here is my u substitution stuff. This means that the series e to the 1 over n squared over n cubed converges by the integral test. Converges by the integral test because my limit came out to be finite. Okay? Go ahead and pause the video. We have 2 more practice problems to do, and then we'll close out. I'm going to try these 2. Determine whether each series converges or diverges using the integral test for convergence. Go for it now, please. Pause the video. All right, let's take a look. Got a series 1 over n to the 3/4. As it increases, this will remain positive, continuous, and decreasing. So we can say the limit from 1, I'm going to remember to change my variables. I'm going to remember 1 to infinity of 1 over x to the 3/4. Congratulations, Markwalter. You've done right this time. The limit then as c approaches infinity of the integral from 1 to c. I'm going to try to speed some of this up then to save some time. X to the 3/4, that's x to the negative 3/4 dx. Alright, this gives us then equals. When I do my antiderivative, I add 1 to the exponent, so that'd be x to the 1/4. I divide by the new exponent, I get 4. This does still have my limit as c approaches infinity in front of there, evaluated from 1 to c. Hard to tell, but that is the limit as c approaches infinity of 4x to the 1/4 from 1 to c. So this gives us the limit as c approaches infinity of the quantity 4c to the 1/4 minus 4 to the 1/4. Now I gotta think through what's going to happen here. Well, as c approaches infinity, c to the 1/4, the 4th root of a growing number will keep growing, so that goes off to infinity minus 4. This grows, this is finite, so this limit goes off to infinity. Therefore, my series, n equals 1 to infinity of n to the 3/4, not 34, 3/4, diverges by the integral test. All right, one more, y'all. Need to check whether or not this series converges. Interesting. Yes, it will be positive as n goes from 1 to infinity. It will decrease because the denominator will grow faster. And it is continuous all the time. All right. I can use my integral test. The integral from 1 to infinity of x over x squared plus 1 dx. Got to think through ways I could take care of this one. Let's see, what are some strategies we could use? We could think through. We could think through u substitution in our heads. See if that would work. So u, the thing that would make sense would be down here, right? If u is that. So if we said that u was x squared plus 1, derivative of that would be 2x. Let's give it a shot. Looks like it might work. All right, let's say that u is x squared plus 1. Let's see, that means du dx is 2x. That means 1 over 2x du equals dx. If I change my endpoints when x was 1, my equivalent to u value would be 1 squared plus 1, so it'd be 2. Oh, I forgot to write out my limit. I'm cheating. 1 to c of x over x squared plus 1 dx. So, when x is c, my equivalent to u value would be c squared plus 1. That's my equivalent u value. All right, so I have all the stuff I need for my substitution. That means then for us, the limit as c approaches infinity, the integral from, I'm going to change my endpoints, I changed it to be 2 to c squared plus 1 of x over u is x squared plus 1 dx. dx is 1 over 2x du. I know some things will cancel out. This is good. So this gives me the limit as c approaches infinity, the integral from 2 to c squared plus 1. Cancel out my x's, divide them away, and then we get 1 over, the 2 will stay down there, 2u du. Interesting. Okay. I'm going to say then my antiderivative here, I'm going to leave the 1 over 2 basically in front here. And I'll get the antiderivative of 1 over u as the natural log of absolute value of u. I'm going to keep my limit as c approaches infinity. It has a half in front there. Absolute value of u evaluated from 2 to c squared plus 1. What does this mean? So this means I have the limit as c approaches infinity of the quantity half natural log of u, absolute value of u, evaluated from 2 c squared plus 1. All right. So I plug in my endpoints, keep my limit, and I get half natural log of c squared plus u is going to stay positive. So I'm just going c squared plus 1 will just stay positive there, minus half times, let's see, when I plug in 2, that'd be the natural log of 2. Alright, so what's going to happen? Half natural log of c squared plus 1 as c goes to infinity. That's going to grow. This is going to stay finite. So my limit approaches infinity. What does this mean for us? Our integral diverges. So my series, the series n equals 1 of n over n squared plus 1 diverges by the integral test. All right. So there we go. There's the integral test and the nth term test for divergence. At this point, I would like you to do the practice problems that are in the packet, the homework there. And there's a couple concepts to do. Don't forget to read all of my posts for announcements and things that might be useful for you, especially regarding any people who want to do retakes and things like that. Please email if you have questions. Be sure you take the check-in quiz also by the end of the day. I'll see y'all later.